Imagine you're trying to grab a ride after a concert, and suddenly 3 other people around you are hitting the same app. 1 minute, cars are arriving in 2 minutes. The next minute, you and 100 others are waiting, and the app is frantically calling every nearby driver. That frantic automatic summoning, that's autoscaling in the cloud, but for servers instead of cars. A few weeks ago, I was at a neighborhood block party. Everyone wanted tacos, and the one food truck had lines that snaked around the corner. When the event picked up, the truck's owner didn't magically clone another truck. Instead, a friend who runs a second truck texted, "I'm on my way," and a volunteer guided people to both trucks so the line moved faster. That little scene is a tiny human version of what happens inside cloud systems when traffic surges. More capacity is brought in to keep things moving. Let's stretch the ride app analogy into a full story because it makes this idea stick. Picture a ride-hailing company called QuickLift. QuickLift has dozens of drivers in a city at any moment. Drivers are like servers. Each one can take a passenger from point A to point B. Passengers are the app requests. Someone clicking buy now, someone watching a video, someone uploading a photo. When there are only a few people needing rides, a handful of drivers handle everything easily. But during rush hour, concert curtain call, or when a celebrity tweets that a store is having a sale, demand spikes. QuickLift's app doesn't wait for customer complaints. It starts calling more drivers automatically, and when the rush is over, it lets drivers go back to their usual streets. That automatic calling and releasing is autoscaling. So what exactly is autoscaling in plain words? Autoscaling is a system that watches how many people need service and automatically adds more resources when demand goes up, then reduces them when demand goes down. It's a way to match supply to demand without a person standing at a keyboard doing the math. The goals are simple. Keep customers happy by reducing wait time, and keep costs sensible by not paying for extra capacity when it's not needed. Now let's map parts of the ride app to parts of the cloud so it stays concrete. Drivers equals servers or instances. Riders equals incoming requests or users. The dispatcher or the app's logic that calls drivers equals the autoscaler, the automated rule set that decides when to add capacity. The part of the app that matches a rider to a driver equals the load balancer. The city's traffic reports, or how long people are waiting, equals metrics like response time, CPU usage, or number of active users. The driver's decision to accept a ride or decline, or how quickly they can pick up a rider, equals how fast a new server can boot and be ready to serve traffic. Let's unpack those plain definitions without the textbook voice. Server, or instance, like a driver in QuickLift terms, it's a worker that does the actual job, serving web pages, processing transactions, or streaming video. It can be a virtual computer in a data center. Autoscaler, the dispatcher that watches the scene and decides based on rules when to call in more drivers or when to send some home. Load balancer, the person at the intersection who points riders to whichever driver is ready next. It spreads the work so no single driver gets overwhelmed. Metric, anything you measure to know how busy things are, like how many people are waiting or how slow responses are. It's the app scoreboard. Scaling policy, the dispatcher's rulebook. If more than 10 people are waiting, call 2 more drivers. Cooldown, the dispatcher waits a little after calling drivers before calling more, so you don't get an overreaction when traffic blips. Let's go through the ride app's morning and evening rush to see these ideas in action. Example 1. The morning rush to a train station. At 7:30 a.m., QuickLift sees a steady rise in ride requests near the station. The autoscaler is watching a metric, the number of unassigned ride requests. When that number crosses a threshold, say 5 people waiting for more than 2 minutes, The autoscaler sends a message to summon 2 more drivers to that hot zone. The load balancer starts routing new riders to those drivers. People get picked up faster, wait times drop, and everyone gets to work on time. After 8:30 a.m., requests taper off. The autoscaler notices fewer people waiting and gracefully reduces the extra drivers, freeing them to do other errands. The system kept the experience good during peak time without paying for extra cars for the whole day. Example 2. A midnight album drop. A popular artist releases a surprise album at midnight, and thousands of fans swarm a streaming site. The site's autoscaler watches CPU usage and the number of active streams. When CPU usage spikes past a safe point, or when many new connections appear in seconds, the autoscaler fires up additional servers. The load balancer spreads listeners across the new servers. If the autoscaler didn't act, the site would get sluggish or crash, and fans would get angry. After the initial frenzy, demand slowly drops, and servers are shut down again. The artist's fans get their music, and the company avoids paying for all those extra servers forever. A couple of important details. Autoscaling decisions are rarely made based on one number alone. The dispatcher usually uses multiple signals: wait times, CPU, memory, or even custom business measures like the number of checkout processes underway. And there's always a bit of lag. A driver needs time to accept, drive to the pickup, and load passengers, and a new server needs time to boot, warm up, and start answering requests. That lag is handled by policies that anticipate trends and sometimes keep a small number of warm drivers already nearby. There are 2 main flavors of scaling to know, explained via our app. One flavor is like asking a current driver to upgrade their car to a bigger one when more passengers hop in. This is vertical scaling, making each worker stronger. The other flavor, and the one most ride apps prefer, is calling more drivers to handle more passengers. Horizontal scaling, more workers, same type. QuickLift generally prefers more drivers because it's easier to dispatch many simple cars than to constantly upgrade one car. Why does autoscaling matter beyond the techie buzz? 2 big reasons: customer experience and cost. If you underprepare, the experience becomes a traffic jam. Slow pages, failed orders, or long waits. Customers leave. If you overprepare, you pay for resources you don't need, like having a dozen idle drivers sitting by the curb all day. Autoscaling finds a middle path. Keep experiences smooth and costs in check. 1 everyday angle. Imagine your neighborhood coffee shop suddenly becomes famous when a blogger posts about it. For a day or 2, the line is out the door. The owner could hire a bunch of extra baristas on the spot, but those baristas would be idle after the buzz fades. Instead, the owner borrows a few baristas from other shops for the busy weekend. That flexibility keeps customers happy without long-term hires. Same idea as scaling servers up and down. Another, think of a family video call for a holiday. Normally, your internet router is fine, but when everyone logs on at once, the router gets busy. If your home network were as clever as the cloud, it would bring in extra capacity for the call and let it go afterward. For a company, autoscaling gives that extra oomph without manual intervention. Before wrapping up, 2 practical notes. Autoscaling works best when applications are built to expect it. If an app assumes the same few drivers will always handle things, sudden new drivers might not have the right instructions. That's why teams design apps to be stateless, so any server can pick up any request, or they store important user-specific info in a separate place so new servers don't have to rediscover it. Second, good autoscaling needs thoughtful thresholds and monitoring, because too sensitive rules can cause thrashing, repeatedly starting and stopping drivers, and that can be wasteful. So let's bring this back full circle to QuickLift and the taco truck. Autoscaling is the dispatcher who senses the crowd, summons more drivers when needed, and lets them go when things calm down. It's the friend who hops in with a second food truck so the line keeps moving. It's the quiet logic in the background that balances patience and speed, customer happiness and cost. When done right, users hardly notice, except that everything feels fast and dependable. If you're picturing servers now, imagine instead rows of drivers pulling up, the app quietly texting, and riders being steered to open cars. That's autoscaling in action. Invisible, practical, and designed to keep the city moving. If you liked this ride through autoscaling, hit like, subscribe, and ring the bell to join Model Drift. More friendly cloud stories every week.